Right, so this is from the other class. So last time we left off, we were on these, when last we left our heroes. They were in the middle of practice problem number 1. And I noticed in my notes that we finished this problem one way. And what I wanted to do was show you another way to do the problem. Because I wanted to show you how you can sum the moments and still get the same answer and break it down into components. Because I showed it on a slide, but it's much nicer to, or it makes more sense, I think, when it's drawn out and when you're taking notes. So hopefully you're taking notes as part of this process. I'm going to move my camera just a tad here. I feel like it's getting too close to this desk seam, which is what I was trying to avoid. All right, so what we're going to do is we're going to take this and we're going to break it down into its X and Y components. And let's look and see, let's see what that looks like. So I'm going to draw this out. I'm going to draw this. Let me draw a wall here first. And then you've got this, this rod sticking out of the wall. And what angle? We're given 30 degrees there. All right, now this is what it looks like. Now we gotta put in some, oh, let me put some measurements in. We know this is a 3-meter length. And we have this force up here. Let's see, 5 kilonewtons. So 5 kilonewtons. I find it much harder to draw a straight line when I'm looking at this paper from below. So let me draw out here. Okay, let me just state more generally, I find it harder to draw a straight line. This is your X direction force. Oh, I should actually draw the force in here. I was drawing the axis to sort of get a feel for the angle. So here's your force equals 5 kilonewtons, right? We have an X component and we have a Y component. So I'm going to draw that Y component like this. All right. Now, we can look at this and we can say the total moment about this point O is the sum of the moments due to the X and the Y components, right? So these really should be some of the moment of the X force about O and the moment of the Y force about O. So let's see how we would do this. Let's look first at the X component. Oh, I don't know why I used a lowercase m there. It's even uppercase in my notes. We are interested in the force in the X direction times the perpendicular distance from the point at which we're interested in rotation about, right? The moment about the origin. The perpendicular distance to the origin. So what is this? Well, the force in the X direction, let me draw this angle in here. We were given here 45 degrees. And this angle here, we're going to need these angles in a minute. This is a 30-degree angle. Since this is 45 degrees and X and Y are 90 degrees to each other, right? This is also 45 degrees, even though it doesn't look like that. That's just because I cannot draw a 45-degree angle very well. And up here you have a 30-degree angle. All right, now what's this perpendicular distance? This perpendicular distance is this distance here. So I'm going to call this perpendicular distance for the X calculation. Now it's actually a Y distance, right? So this is the perpendicular distance. This is D perpendicular for X. Now, geometrically, we can see, let's write this out. This moment about the origin due to the X component is equal to the X component of force. Well, what is that? That is the force, 5 kilonewtons, times, here's an angle 45, right? The adjacent is cosine. So here we've got 5 kilonewtons times cosine 45. This is Fx. Now I'm going to multiply this by d perpendicular of x. That's this height right here, right? And my triangle, I have a 90-degree triangle, because this is the line of axis of the force, and this is the point at which it's perpendicular to the origin, right? That's why we're taking this distance. And the distance is, let's see, I've got 30 degrees, I've got the hypotenuse of the triangle, so I've got hypotenuse times sine of 30 gives me the opposite, right? So here I'm going to write 3 meters times, let me put some more brackets here, sine of 30 degrees. And this is my perpendicular distance. For the X component of force. So this is the perpendicular distance from the point of rotation to the line of action of that force. And if I solve this, I wind up with the moment about the origin due to the X component. I really should have reversed these. Is 5.303, and I've got to look at this. Which direction do I ascribe to this? Is this X component generating a clockwise or counterclockwise moment about the origin based on its location, how it's acting? Clockwise or counterclockwise? No chat answers. All right. So
clockwise?
Yeah, clockwise, yes. So look at this, right? One easy, it's kind of hard to visualize it out here, but if you look at it, the line of action perpendicular to the origin, right? You can clearly see that if there's a stick here, right, it's gonna act the same way. It's gonna act clockwise, right? So this is a clockwise moment. Let's do moment in the Y direction, or moment about the origin due to the Y component. Let's call it, let me fix the subscripts now. All right, so now we have the Y component of force times the perpendicular distance. This is from the origin again to the Y force line of action. And you can see the line of action for y is running like this. So our d perpendicular y is actually this distance up here. Let me, how am I going to do this? Let me just draw. I have a little more room. That's my perpendicular distance from the point that we're interested in the moment about to the line of action, right, of the y force. That's the distance. I didn't draw it down here just because it's going to get crowded, but that's basically the same distance. All right. So what are these? These are. Let's see. I'll just go continue over here. All right. The y component of force is now. Now you could use the cosine. Well, yeah, use the cosine function basically again. Or you can use the sine function. You know, you're kind of in luck here because it doesn't matter if you use sine or cosine. You could get this wrong and still wind up with the correct the correct answer. So 5 kilonewtons. If we're looking at tip to tail, right, you're using sine. If you're just drawing it like the way I drew it, you can use cosine. It doesn't matter. This is sine 45. This is your force, your y component of force. I'm going to use sine because I know someone's going to come back to their notes and be like, why did they use cosine in the same, you know, both times? All right, now I've got my distance, which is 3 meters. And here it makes a difference, right? You have to use cosine of 30 or sine of 60, right? To get this distance here. Yeah, oh, I said cosine of, yeah, let me just write cosine 30. Right, so this is the part of the problem where if you don't know sine and cosine yet, you're going to have a problem here. So here we wind up with the moment about O due to the y component of force is 9.186. And this is also generating a clockwise moment, right? So now the total moment about O is just the sum of the components which is what? I've got 5.303. And now you could use negative signs instead of you know, the arrows just to keep track of things. You want to keep track of which direction things are going. Right. So your moment about O is just 14 point. I mean, this is going to round up, right? You're going to have 14.489. So this will also be 14.5. So 14 point, what did I say? 48998, yeah. So 14.5 kilonewton meters. Oh, you know what? I forgot my units on these. Each of these individual moments has units, right? This is the reason I put the units in here and then I forgot to write them. Kilonewton meters, kilonewton meters, kilonewton meters, and again, clockwise is your rotation. So now this is a little more of a complex, like this takes a little more time in math to do it, but you may be in a scenario where maybe you can't, maybe it's easier to break it down in X and Y than to actually do the, get the perpendicular distance calculated. But this is another way to do it. And either way is correct, right? It's not wrong to do it one way or the other. It's just, it might just be faster depending on the information you're given, to do it one way or the other. All right, so that's now, and this is actually more analogous to if you had two forces acting on the point, right? You might want to break it down in X and Y. If you did have two forces, you break it down to X and Y. You can come up with each of their components, add them together, and then figure out the sum of the moments that way as well. Any questions about this problem? Let me see. This is another example. So this next one is an example of where you would probably want to break this down. I'm going to go back to the PowerPoint in a minute, or a couple seconds, just so we can see this thing a little better. For some reason, my printer is not printing these as clearly as when I did it at college. I wonder, oh, smaller. Yeah, it's about the same size. So my laser printer is obviously not as good as the one at school. The bracket shown. Determine the moment of the force about point O. Now look at the information we're given. We're given this beam that's 5 meters long in the X direction, and then it's 2 meters up. And we're given a force that's acting, and we're not even given the angle, we're given the slope, right? It's a 3, 4, 5 triangle. So we have geometric information. So we're going to use this to figure out our force components. So this is an example where it's probably going to make more sense to break this down into X and Y than to try to take and extrapolate this out and try to figure out what's that distance. Right now you got this really funky shape. Yeah, I suppose you could do it with a triangle here, but it's just easier to do it X and Y. So let's do it that way. Let's go to the document camera. Okay. So let me draw this over here. How am I going to do this? I'm just going to draw a stick figure. That's what I'm going to draw. All right, so we've got 5 meters. Before I label anything here, I'm going to put in my other components. So this is my force. And this is the 3, 4, 5. Oh, I should have used different color. Slope. Well, 3/4 slope. Over here, I'm going to do the breakdown at this point here because, again, it doesn't matter if you have an X and a Y this way, right? Or an X and a Y over here. So I'm going to draw these like this. And I'm going to draw the line of action through this so we can kind of see the how it goes. Make this nice and solid. All right. So this is relatively straightforward in that we can find the X and Y forces using the ratios of this triangle, right? This is really the same thing as looking at this as, I'm going to draw the force out here separately just because I think it's clearer. I'll use black again. Oh, no. These are the X and Y components making it up, right? And this is a 3. Apparently I drew this the wrong way, but it's 3, 4 this way. So we can write out the forces as a function of this similar triangle, right? This is the small triangle, and this is the big triangle that has, you know, it's basically similar, right? It's 3, 4, 5. Oops, I forgot the hypotenuse here. This hypotenuse of 5 corresponds to 100 newtons, right? And each of these sides corresponds to the force. So we can just say the force in the x component of force is equal to 100 newtons times 4/5, right? 4/5, similar triangle. Again, I didn't draw it so that it looks correct, but you know, that's oops, force y. That's what happens when you draw this stuff out. And remember, never assume a diagram is to scale unless it tells you it's to scale. Oh my God, that's 100 newtons. 3/5. This gives us 60 newtons. So now we have two components of force, x and y, right? Now the perpendicular distances are easy because we've got, 2 meters here. But how can I say 2 and write 3? I had no idea. Here's our O, 2 meters. So now our moment, right, about O is going to be the sum of the moments so I've got the x component of force times the perpendicular distance plus the y component of force times its perpendicular distance. I'm kind of hesitant to use the x, y subscripts on this because notice, I want you to notice the perpendicular distance for the x component of force, right, is the y direction. If we look at this line of action for the force, right, it's 2 meters perpendicular to that origin. So here we have the x component of force, which is 80 newtons, times 2 meters. And what's the sign? Well, the x component of force is generating a clockwise rotation. And remember, our sign convention is this. Positive is counterclockwise. So this is going to be a negative. Turn that into an arrow. This is a negative. This moment about the origin based on the x component of force is negative because it's it's clockwise. Now I'm going to put a minus sign here because I don't know what it is. Here we've got the y component of force is 60 newtons. And the perpendicular distance here is the line of action up and down is 5 meters, right? And if we look at this thing, this force, this y component of force, oh, what the heck? All right, so sorry about that. My mouse pen, wow, that's crazy. My mouse pen went a little nuts. What was I saying? Oh yeah, this perpendicular distance is 5 meters, and that's the line of action of force. This force is also generating a clockwise rotation, right? So these individual components are clockwise, which makes their signs negative. So I'm not going to turn this into a positive sign. I'm going to leave it as a minus. So the overall moment is just, what do we got? We got a negative 160 Newton meters minus 300 Newton meters. And this gives us a moment about O of 460 So notice, right, this turns out to be a minus 460 Newton meters. And I'm going to rewrite this as 460 Newton meters with a clockwise arrow. Right? Or you can write out clockwise. So this is, again, keeping track of directions. And the way we do that is we use signs. The arrows are okay. They're fine for reporting an answer. But at some point, once you start having to do math with things and add things together, you're like, okay, well, if I had two opposing ones, I'd have to know the sign so I can figure out which direction is greater. You may be doing a problem where you have multiple sets of moments you're summing, like 4 or 5 moments, and you're like, well, which way is which, right? Arrows becomes really messy. So you want to pick a sign convention. The sign convention we use in this class is counterclockwise rotation is positive. I don't actually know. That probably came from the right-hand rule in physics. So, coming out of the page. But this is a positive moment, counterclockwise. So when we do moment calculations, we look and see which direction things are going. If they're clockwise, they're negative. If they're counterclockwise, they're positive. That way, when you add them up, you have a sign convention you use. Now, you could pick the opposite sign convention. As long as you keep track of all your signs, it doesn't matter. Your final answer will still be 460 Newton meters clockwise, right? That's still the result of this problem, physical result. Any questions about this problem? All right, so let's see. I'm going to take this, go back to the PowerPoint here. Oh yeah, so couples. This is what is a couple? Well, it's not. I was trying to think of a good joke. It's not like a married couple. It's two equal forces acting in opposite directions. That is sort of like a ideal. It's sort of like a ideal, non-ideal married couple, right? Ideally, both people in the marriage have equal say. However, opposites attract, right? So you wind up with with two forces acting in opposite directions. I feel like this is how my wife and I are sometimes. And they're separated by a perpendicular distance, right? So you have this force 1 and force 2, right? They're acting in opposite directions, and they're separated by this distance, this perpendicular distance, the sum of these two radii, and they're generating a torque. And this is kind of where the sign convention comes from. See this torque? This is a vector. When you have a vector acting, in a plane like this, you have what's called this cross product of vector action. And that's really what's happening. It's the cross of this force vector with the distance vector. It gives you a cross product. And if any of you have taken physics, do you guys remember the right-hand rule in physics? Where you have, I can't even do it. Oh, you know what? I'll use my, turn this light off, zoom out. In physics, you have this right-hand rule where it says you take your right hand, and if you have two vectors, one's acting this way, and you cross it with another vector acting this way, right? The cross product of those two vectors looks like this. You do this curling motion, and the resultant vector is where your thumb is pointing. So this rotation gives you a positive z, right? The reverse rotation points downward, and it gives you a negative z. So that's why clockwise is negative, right? and counterclockwise is positive. So that comes from your right-hand rule, which I think I talk about on this next slide here. Anyway, that's where it comes from. That's where the sign convention comes from. But notice, right, you can have the geometry itself could look like this. But notice the lines of action of these forces, the perpendicular distance, the moment, right, is calculated by this perpendicular distance. And let's go to the next slide here. So this is what the criteria are for a couple. First of all, that they're equal in magnitude, the two forces. The forces have to act in opposite directions, and they're separated by some perpendicular distance, right? So two forces in line with each other acting in opposite directions, they're just going to cancel out. So a couple moment is this. It's force times distance. It's the perpendicular distance between those two forces, but it's one of those forces. And you can actually show you wind up with like this answer, oops. This is force times the total distance, right? If you did each individual force times half the distance and added them together, you'd wind up with this, right? Force times the total distance. Let's see, forces, yeah. So as long as the couple, so what do we talk about equivalent couples? Couples are equivalent if they produce the same moment, right? The forces, the perpendicular distances, they can all be changed. So you could have a force of, say, I don't know, 1 Newton acting at 10 meters apart, right? Which is the same couple as, what did I say? I said 1 Newton acting 10 meters. So 10 Newtons acting at 1 meter, right? So it's the same couple. Yeah, and if that's the case, right, the couples are equivalent. That's all this rule is saying. Properties of the couple, a couple moments unaffected by the pivot location. So if you're given a problem where it tells you that there's a couple acting on this beam of whatever the moment is, you don't, let's see, do I have an example of that? No, I don't. You don't have to worry about the location. A couple already takes into account force times distance, right? So you've got that baked into the couple. And let's see, equivalent couples have different force and perpendicular distances, but produce the same couple moment. Yeah, this is just the same thing we covered in the last slide with the equivalent couples. All right, so we got some practice problems here. Let's see. Oh, this is the end of module 3. So module 3, if I recall, was pretty quick. So let's go through these problems. In terms of slides, it was pretty quick. I'll probably even get to module 4 by Friday. I have to look at my notes. All right. Module 3. All right, the first one here, let me again point this out on the PowerPoint. We've got a beam that extends out from some fixed surface, and it says determine the resultant couple moment acting on the beam shown to the right. So what's the couple moment? And let's look at this thing before I go to the paper to look at this. I've got, I'm going to look for, first of all, I'm going to look for forces of equal and opposite magnitude and direction, right? So I've got one force couple here, 300 Newtons acting up and 300 Newtons acting down. And those are perpendicular to one another, or well, they're parallel to one another, so they have a perpendicular distance between them. Same thing with the 400 Newtons here and the 400 Newtons there. Pointing down, pointing up, parallel to one another, perpendicular distance of 2 meters. And then I've got this 200 Newton force couple. And this is also 2.2 meters apart, perpendicular distance. So we're going to go through that real quick. And oh, I zoomed out for the right-hand rule demonstration. Okay. So remember, a moment is a force times a distance, this perpendicular distance. And our notation is always counterclockwise is positive. So it's important to remember that. So let's look at the couples we have. Let's call this couple number 1 up here, the 400 Newton. So C1 is going to be 400 newtons times 2 meters, right? These are the forces, and the perpendicular distance between them is 2 meters. And I want you to see which direction is this creating, a counterclockwise or a clockwise moment, this couple. Right. This is, notice it's like you're turning a wrench, right? With 2 hands, or turning a wheel with 2 hands, right? You're turning this is like I'm turning something counterclockwise. So this is counterclockwise, it's going to be a positive, right? So this equals 800 Newton meters. That's positive. C2. Let's call the 300 Newton one number 2. All right, number 2 has 300 newtons acting at a perpendicular distance of 5 meters. So 300 newtons, 5 meters. Now, this set of forces wants to create a clockwise rotation, right, which is a negative. I'm going to put that negative sign in there. So we wind up with C2 is equal to a negative 1,500 Newton meters. Just underline these. So that's right, and that's a clockwise rotation. And finally, we've got couple 3, which is acting over here. We can see the forces. 200 newtons. Let me label this couple 3. And they're 0.2 meters apart. And they're also acting, let's see, this is going to generate a clockwise rotation. So this is a negative 200 newtons times 0.2 meters. And this gives you, negative 40 Newton meters, couple 2. So the total couple, or total couple moment is just the sum of these, right? So we've got 800 well, I'll just put the minus signs in here, plus a negative 1,500 plus a negative 40. And this equals, we got 800, we got minus 1,500 minus 40, we get a negative 740 Newton meters. So we can say the resultant couple moment is equal to 740 Newton meters clockwise. Oh, I cut my answer off. I have enough time to get through this last one. Maybe. No, I probably don't. It's about the same. No, it's got more. Yeah, we'll just do this this other one next time. If you want to take a look ahead at example 4 and do it, see if you get the same answer. That'd be useful for asking if you have any questions to ask. Any questions so far about moments and couples? I'll stop recording here.